who aims to understand the origins of the solar system and the conditions that allow life to evolve on Earth. In particular, she studies the magnetic field of stars, since these power both the hot X-ray emitting corona and the supersonic wind that together can ionize or erode a planet's atmosphere. She joined the University of St Andrews in 1995 and became a professor there in 2010. So whenever you're ready, Moira, you can share your screen.
I like the confidence with which you say you can share your screen.
I believe in you.
Hopefully this will all work. There, I'm hoping you can see my screen now.
Yep.
Okay. Right, so hopefully that is all working. I can no longer see any of you. So if you want to snore quietly in the background, you can do. So I'm going to talk today about a particular type of prominence. They're called slingshot prominences, which we see on sun-like stars that are rotating rapidly. And this talk is about how we use these prominences to learn about the structure of the coronae on these stars and to learn about their mass loss. So those of you who are solar people might look at this little cartoon with the prominence shown here. Oh, now Paul showed me yesterday how to get a laser pointer. So, oh, here we go. This thing here is a slingshot prominence. And hopefully by the end of the talk, you'll understand why it's appearing in a field structure that you might otherwise find a bit surprising. But let's start by looking at the sun and what we know about the sun's coronal structure. This is a beautiful 2D image of what is a very three-dimensional structure. We can see the closed magnetic loops here confining the coronal gas. And we can see these radial structures here, which are the open field lines where the sun is losing mass in its wind. But of course, the sun doesn't always look like this. The sun changes through its magnetic cycle, and its coronal magnetic field and its wind change as well. So if we look at different parts of the sun's magnetic cycle, if we look on the left here, these are two more eclipse images. So on the top, we're at cycle minimum. We can see the emission from these closed regions, these beautiful helmet streamers, which are overlying the active region belts, where we find most of the spots on the sun. And we find the dark regions over the open field at the magnetic poles. We see a much more complicated picture at cycle maximum when there are most spots on the sun, and the suns are distributed to a greater range of latitudes. And we see the emission extending over a much broader range of latitudes as well. It's not just the structure of the magnetic field and its associated plasma that changes, however. If we look at the two right-hand images, we can see how the solar wind changes. So these are each composite images. If we look at cycle minimum, there's an image which is an X-ray image showing the hot emitting gas of the corona. You see it's mainly close to the equatorial plane. Overlaid on this are contours here showing the speed of the solar wind. So this inner contour here is about 300 kilometers a second, and we see that over the closed field regions on the sun, close to the equator, we have the slow wind, and the fast wind, which is at about twice, slightly more than twice the speed, is emerging from the polar regions. And the colors here just denote whether it's outward pointing or inward pointing. That's the sun's magnetic field. If we look at cycle maximum, we see a much more complex structure in the X-ray image, and associated with that, there's a much more complex structure in the wind speed. So we see wind speeds that vary between high and low at almost all latitudes. So, you know, for an astronomer, it's utterly sickening to see these beautiful images because we know so much about the sun. And it's like the old adage, the more you know, the more you realize that you don't know. But at least for the sun, we have direct images. But this is just how the sun evolves on timescales of decades. We imagine, although we don't know, that the sun's magnetic field has changed as the sun has evolved. We can imagine this because the sun's rotation rate has changed with time as it has evolved, and rotation is what drives the dynamo. The dynamo generates the magnetic field. So we can see the effect of this changing angular velocity here in this plot. So what we're looking at is angular velocity in solar units against age. So this is age in millions of years. So we're here today, 4,500 million years. That's the Earth's age. And what you're seeing are models for 3 different stars. One that started off rotating quite rapidly. It was the 90th percentile of a distribution of velocities. One that was rotating with a moderate angular velocity and a slow rotator. What we see is that initially, when the stars still have a disk, the first 10 million years of their lives, the angular velocity is pretty much constant. The presence of the extended disk around the star, linking into the magnetic field of the star, keeps its rotation almost constant. But the disk dissipates, it forms planets, it accretes onto the star. When the disk disappears, the star spins up. You can see that here. The star is still young, it's still contracting, so it spins up as it contracts. Eventually, a radiative core forms, the star stops contracting. At this point, it has enough of a wind, it's generated enough of a magnetic field that the wind removes angular momentum from the star and spins it down. And we see then this long, slow spin down that carries on onto the edge of the Earth. And it's similar for the tracks of the other 2 stars. So we expect that the sun was a much more rapidly rotating star when it was younger, and we therefore expect it generated more magnetic flux and was more magnetically active. This is quite a difficult set of models to test, however. I'm only showing you one set of model tracks here, but I could have shown you lots of other ones. We've got indirect ways of testing this rotational evolution by using open clusters. So for example, here's the Pleiades here, here's H pair. Within each open cluster where the stars are all of the same age, we have a distribution of rotation rates, so we can plot a range of angular velocities on this and use that to test these rotational evolution models. However, the gold standard would be to detect the winds of these stars. It's a really, really hard thing to do. It's not impossible, but it's very, very difficult. And that's because these winds are very tenuous. They're not like the winds of massive stars. They're very tenuous. They're very, very hard to detect observationally. So this is one of our great puzzles when we think about solar-like stars, is trying to understand their rotational evolution and to understand their winds. The other great puzzle that we're faced with is thinking of what sort of magnetic fields do they have. And I've got 4 examples here of just 4 different stars that I chose. So what you're seeing is the radial component of the magnetic field at the surface, plotted in Gauss. So if you look at the top left, here's Epsilon Eridani, which has got a field that looks rather like a tilted dipole. And next to AD Leo, almost everyone's favorite flare star, which has got a large-scale field that's rather like an aligned dipole, but a much, much stronger field. The 2 stars on the bottom are very famous planet-hosting stars, HD 189733 and Tau Boo. They're very different stars, but they both host planets, and they both have rather more complex magnetic fields. Now, of course, stars are point masses to us. For most stars, we can't resolve their surfaces. So it's a reasonable question to ask, well, how can you infer the structure of the magnetic fields on these stars if you can't resolve their surfaces? Well, we use a technique called Zeeman Doppler imaging, and it uses the Zeeman effect. So we know that in the presence of a magnetic field, some lines will be split by the Zeeman effect into the left and the right circularly polarized components. And the difference between these is the Stokes V signature. Now, Stokes V is sensitive to the line of sight component of the magnetic field. So if you look at the little animation on the right here, I've painted a little patch of radiomagnetic field on the surface of this star. And underneath you see a movie of what we would detect as the Stokes V signature. So if this is a radiomagnetic field, its greatest line of sight component is when it's at disk center. And you can see the amplitude of Stokes V is greatest when our little patch of field is at disk center. And it's least when it's on the limb. Now, this method can only detect the very largest scale fields of stars. And you can imagine if you had multipolar regions that were very close together, their polarities would cancel out, and we would infer there was no magnetic field there, even if the fields were individually quite strong. We can do a similar thing by painting azimuthal field on the surface of the star. Now, in this case, the line of sight component is greatest when our patch of field is on the limb. So we see the Stokes V signature has its greatest amplitude at those times. And in fact, it switches polarity. As the patch comes towards us, the polarity is one way, and as it recedes, it's in the opposite direction. So by looking at the Stokes V signature as a function of time as the star rotates, we can use both its amplitude and its variation with phase to infer the structure of the magnetic field. And there's an example here on the right. This is actually V374 PEG, which I'll talk about later. What you're seeing is velocity on the x-axis here, and this is rotation phase, or equally you could think of this as time. And we've simply stacked up in time all the different spectra, and you can see the Stokes profile, Stokes V moving through the line here. We fit this data with spherical harmonics. So the Stokes signatures are fit by these three coefficients, alpha, beta, and gamma, which you can combine to form the three components, the three vector components of the magnetic field at the surface of the star. Now, as I've written underneath here, these two components describe the poloidal component of the field, and these terms describe the toroidal component. And I've made a little cartoon here to illustrate these two. If you have an azimuthally symmetric system, then you can think of the toroidal component as being azimuthal. So this would describe the underlying azimuthal field on the sun that produces the spot belts. That would be the toroidal field. And the poloidal field lies in meridional planes. Now you might think, what's wrong with BR, B theta, and B phi? They're perfectly good field components. Why would you bother describing a magnetic field in terms of a poloidal and a toroidal component? Well, there are many good reasons, but one of the best ones is that they're a great way to describe helicity. Helicity can be described very cleanly and intuitively as just the linkage between the poloidal and the toroidal fields. So I have another little cartoon on the right here to explain this. The toroidal field lines are shown in blue, and they lie on spherical surfaces, so they have no radial component. The poloidal field passes through a spherical surface, and in particular, at the surface of a star, the poloidal field passes through the surface. So the radial component of the poloidal field links through the loops of toroidal field. The other two components of the poloidal field, the theta and phi components, don't contribute because they lie on spherical surfaces. So the flux of the poloidal field that links through the toroidal field describes the helicity. And I've shown the expression for the helicity at the bottom here. So why do you care about helicity? Well, it's a conserved quantity in a magnetic field, and so it gives us a great deal of information about how the field is evolving with time. It's an output of many dynamo codes, and it tells us something fun about how magnetics behave. And I guess one of the easiest ways to think about this is if you think of the, magnetic field erupts from the interior of its surface out of the corona due to the gas to produce the hot emission you can see in this image. So stars can lose all the energy, most of the energy that comes out of a magnetic field by radiating it away. So radiation will allow the star to lose energy, but the only way the star can lose its helicity is by ejecting it in coronal mass ejections. So there's a huge body of work involved in looking at the state of the sun's magnetic field and the coronal mass ejections that it produces. So what do we find when we look at other stars? Well, we can't measure observationally the helicity of stellar magnetic fields because it's a volume integral and we don't observe the magnetic field throughout the volume. We only observe it at the surface of the star. But what we can evaluate is the helicity density. So that was the integrand of that integral I showed you a few pages ago. So this is a plot of the helicity density determined by mapping the magnetic fields of stars against the B squared for the toroidal field, which is a measure of the energy in the toroidal field. So each point here is a star. In some cases, we have multiple measurements for each star, and those are the very pale symbols. And symbols with a dark line around them are the average of all the measurements we've made. You notice they're colored, these symbols, and the color denotes the mass of the star. So a very pale color is a low mass. These are all low mass stars, and the darker colors are closer to the mass of the sun. These yellow points are actually the sun, and the numbers 1, 2, and 3 are just averages taken at different phases of the sun's magnetic cycle. So we can see from this cloud of yellow points how the sun would move in this particular parameter plane. Now, the one thing that comes out of this, and if you note it's over 8 orders of magnitude in energy, is a beautiful correlation that the helicity in a stellar magnetic field on the large scales that we can measure correlates beautifully with the energy in the toroidal field. But there's another trend as well, and that's with the stellar mass. You can see that the triangles denote stars whose masses are less than half a solar mass, and the circles are the larger masses. So we see that all the very lowest mass stars are up at this end of the plot. Now, this is the sort of correlation that, as a theorist, really warms your heart, particularly when you see the sun through its cycle lying within the spread of the data points. But we see something rather different if we plot the helicity density, not against the toroidal energy, but against B squared for the poloidal field. And now we see that beautiful straight line correlation has split into two. And the two branches are distinguished by the masses of the stars. All the stars, or most of the stars, with masses above half a solar mass lie on this branch, and the other branch is the lower mass star branch. So what we see is that if we choose some helicity density, there are two possible values of the poloidal energy. You can either have a low energy state or a higher energy state for the same helicity. Now, that's interesting. So in order to try to understand this, we really need to look at how the magnetic field is structured. So let's pick two examples. Let's take this star here, which is on the higher mass branch, and this star here on the lower mass branch. Now, one of the things that separates these two branches is probably the nature of the dynamo. The higher mass branch is composed of stars that will all have a tachocline. They're all capable of driving an interface dynamo in the same way that the sun does. The stars on the lower mass branch don't typically have tachoclines. Certainly the lowest mass ones of them don't. So they probably have a different type of dynamo. So perhaps This behavior shouldn't surprise us, but the exact nature of it was surprising. So let's look at these two stars and compare their field structures. And here's just a reminder of what helicity measures. It's the linkage of the poloidal field through the loops of toroidal flux on the stellar surface. So what I'm going to do is I'm going to show you contours of the toroidal field and overlaid on that a color map which tells you the strength of the poloidal field. So here's our higher mass example, GJ49. So the contours are toroidal field lines, and the dashed and the solid are different polarities, and the color is telling you about the strength of the radial component of the poloidal field. What matters here is that you can see that the purple color lies within contours. So most of the poloidal field lines are coming through toroidal loops. They are very well aligned. Now, before I move on, I just want you to notice the scale here for BRs and Gauss. It goes up to about 30 Gauss. So GJ49 doesn't have a terribly strong field. Let's have a look at its partner, which had the same helicity density. So this is GJ1245b. You notice the radial field is an order of magnitude stronger, but it gives the same helicity density. The reason is that if we look at these loops of toroidal field, they're enclosing poloidal field that's of two opposite polarities, and they essentially cancel out when we determine the helicity density. So because the toroidal field, and indeed in this case the poloidal field, are no longer axisymmetric, they don't line up well, and so although you have lots of magnetic energy, you haven't got a lot of helicity. So what we find is if we take the ratio of the helicity density to the energy density, and there's a factor of the radius of the star in here to keep the units right. If we plot this against stellar mass, the lowest mass stars are inefficient at producing helicity density. They've got less helicity density for the same energy compared to stars like the Sun, which are capable of generating much more helicity. So there's clearly something different about the very lowest mass stars. And if the magnetic energy is essentially what drives the X-ray emission and the flaring that we see, the helicity density might have something to do with the rate at which mass is ejected. And there's clearly something odd about the low mass stars. Now, one of the difficulties in observing other stars is we only observe the magnetic field at the surface. So we only get the helicity density, which is measured at the surface. If we want to fully understand the structure of stellar magnetic fields, we need to understand how they can be extrapolated out into the corona. And there are many different ways of doing this. Here's GJ49 again. On the left is a potential field extrapolation, and on the right is a non-potential field extrapolation. The surface magnetograms were the same, the radial field is the same at the surface, but the coronal field is very different. So given that there are many models that fit the data just as well, how do we distinguish between them? So this is my second puzzle. The first puzzle was about stellar winds, and the second puzzle is about the overall structure of the coronae of these stars. So, given that when I was talking to Brian yesterday, I discovered he's from East Kilbride, he's a fellow Scot. So I thought I'd put in a culturally appropriate analogy here for stellar prominences. So for those of you who are not Scottish, what you're looking at is a favourite Scottish pastime. Obviously, this is what I do on my weekends. And it's throwing the hammer. So that the gentleman in the yellow t-shirt has got a very heavy iron ball here attached by a chain to his hand. He spins round and round and round. And at some point he lets go, and the trick is to see who can throw it the furthest. And this is how we imagine slingshot prominences behave. The star is the man in the yellow shirt. The prominence is the iron ball, and the chain is the star's magnetic field. As the star spins, the prominence co-rotates with the star until eventually it escapes. So why is this useful to us? Why am I showing you this? It's because by observing these slingshot prominences, we can learn about coronal structure and wind mass loss. So here's how we do it. On the left is an image of a rotating star, and here's a prominence trapped in its corona. So as the star rotates, the prominence passes in front of the star from left to right. And underneath here is a part of the stellar spectrum. This is where we see H alpha. On these stars, H alpha is filled in almost a continuum, so it's almost flat. But this prominence here is scattering H alpha photons out of the line of sight. So when it's here, it's scattering out of the line of sight photons that were coming towards us, because this part of the star is coming towards us. So we lose photons that were blue shifted. As the prominence moves into line center, we lose photons in the center of the line. And as it moves on to the right-hand limb, it scatters away photons that would have been redshifted and would have contributed to the red part of the line. So if we take all these spectra and stack them up in time, we see these absorption features moving from blue to red through the line. And it's by tracking these that we can infer the locations of the prominences. So this is what we actually see. This is a very famous star called Speedy Mick. Its real name, of course, is BO Mick, but everyone calls it Speedy because it rotates very rapidly. And you're seeing here two different observations made one night apart. So this again is velocity, or equally wavelength, and this is rotation phase, or equally time. And these dark features here are the prominences moving through the line profile. The time it takes the prominence to move through the line profile tells you its distance from the rotation axis directly. So we see on Speedy Mick on this night, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 prominences in view. If we look one night later, some of the prominences are still here. This feature is still present. This feature marked B has disappeared. I think there might probably be new ones that have appeared. This thing here has appeared from the night before. So we can see that there's a recurrence timescale of about 1 day, about 24 hours. We see these types of features on many different types of rapidly rotating stars. This is an example of a young star. It's only about 8 million years old. Again, it's a rapid rotator. It's at a very interesting stage in its evolution, where it's at the boundary between being fully convective and just about to develop a radiative core. So it's at a very interesting evolutionary stage. What you're seeing here is an image of the spots on this star, and you're looking down on the rotation axis. So the solid line here is the limb of the star, and these dashed lines are 30-degree latitude intervals. So you can see it's a very heavily spotted star. And you can see here the prominence tracks going through the H alpha line. So even in very young stars, we see evidence of prominences. This one even had the grace to produce a prominence at just below the predicted maximum height at which they could form. So I think this is one of my favorite stars. There are some stars for which the rotation axis is pointing almost directly towards us as the observer. So we're looking down the rotation axis of the star. In this case, we see prominences not in absorption, but in emission. And so this is prominence signature seen in velocity space, but equivalently it's essentially showing you their location as you look down on the rotation axis. And what we find is that the prominences, these dark features, they cluster around one particular radius, which is the co-rotation radius. And in a rapidly rotating star, the co-rotation radius is simply the equatorial radius at which the centrifugal forces begin to dominate over gravity. So the effective gravity changes from pointing inwards towards the star to pointing outwards. And it's at this location that we find prominences. And once again, you can see these are observations taken 4 nights apart. The overall distribution of prominences is similar, but their locations have changed. So again, we see a time scale of about a day or a couple of days for the distribution to alter. I'm just going to show you one more example because this is a particularly nice one. This is V530 Per. It's also known as AP149, one of the alpha Per stars. This is an HR diagram here, luminosity against temperature with theoretical evolutionary tracks on it. So the black lines are evolutionary tracks for stars of different masses, and the blue dashed lines are equal time intervals. So this is where we think this star lies. There are 2 different possible solutions for it. It looks as if it's about the mass and radius of the sun. So it's a nice analog for a young sun, and it just hasn't quite got onto the main sequence yet. So it's still pretty young. Again, we see beautiful prominence features in the data. These are taken about 6 nights apart. And once again, you see here the prominence distribution clustering around the co-rotation radius. And 6 nights later, the distribution has altered slightly, but it's similar in overall appearance. So I've just shown you a couple of examples just to give you a flavor of the types of things that we observe. But we see slingshot prominences very commonly on rapid rotators. They have to be rotating rapidly enough that the co-rotation radius is close in. So what about not mass that is confined within the corona, but mass that is being ejected, more like a coronal mass ejection that we might see on the sun? So this is an example of a low mass star. This is V374 PEG. It's just about 1/3 of a solar mass. And we see both types of behavior on this star. So here we have the H alpha line here. It's stacked up in time. These little triangles denote all the observational phases when observations were made. So you can see it was very densely observed. Within the line here, we see signatures of prominences. And in fact, this color table is inverted. The brighter shade is actually the prominences. So we see prominences at these phases and here. So that's within plus or minus V sin I about 36 kilometers a second. But we also see these absorption features out in the blue wing with maximum projected speeds of over 600 kilometers a second. So these are features that we interpret, or were interpreted by these authors, as being material ejected from the star. So we see both confined and also ejected material. So there's been a concerted effort to look for the equivalent, the stellar equivalent of coronal mass ejections in other stars. These are results of a large survey done of about 25 M dwarfs, done by Christine Vida. And what you see plotted are the line asymmetries, the velocities of the line asymmetries in H alpha. So this is all the velocities that were to the blue and all the velocities that were to the red. So both were seen. So this is the distribution of velocities over all the stars, the 25 stars, many of them observed many times. So there's over 5,000 individual spectra. The right-hand side are the inferred masses of the ejected material. Now, these velocities are typically below the surface escape velocity. And so these authors felt that in many cases this was not ejected material, it was material that was disturbed but not ejected. But in some cases, the velocities were indeed high enough that it was possible to interpret these as coronal mass ejections. There was another study of slightly higher mass stars, 425 F to K stars, by Leitzinger et al. They didn't see any equivalent coronal mass ejections, but they did comment that their observing timescales had perhaps been too short to catch coronal mass ejections. So this brings us to the very, very interesting relationship between coronal mass ejections and flares. And this is a plot that goes back to Jeremy Drake in 2013. So this is the kinetic energy against X-ray flare energy for, well, the red triangles are solar flares, and the other symbols are for stars. And the point that was made in the Drake et al. Paper was if you extended this lovely correlation from the solar events out to the typical X-ray energies we see for stellar flares, you would predict an absolutely enormous kinetic energy for stellar CMEs, a ridiculously high amount of energy. So they suggested that it must be the case that this relationship that's so well defined for the sun does not extend to other stars. And indeed, these more recent measurements of CMEs and other stars seem to suggest that other stars do not produce CMEs of a kinetic energy as large as you would expect by looking at the sun. And if you're interested in the evolution of solar systems and exoplanet atmospheres, the impact and the effect of CMEs is something that is of great concern. So how do we test this? Well, we can take the Zeeman Doppler images, we can extrapolate the magnetic fields. This is a potential field extrapolation, but there are other ways to do it. And we can look for stable locations within that field. So sites where material could accumulate. These are sites where, in order for material to move along magnetic field lines, it would have to be climbing out of a gravitational potential. So these are gravitationally stable mechanical points. So if we allow material to collect at these points, we can predict where mass can be supported. And these red dots here are all the stable points in this magnetic field. This is Abdor, the star. So here's what we would see in time as Abdor rotates. So the black lines are magnetic field lines, and the red blobs are the predicted prominence locations. And on the right, we see the H-alpha spectrum developing in time as the star rotates. So we see these features moving through the spectrum. And these are indeed the typical prominence features that we would expect to find. So this is a prediction made on the basis of the observed magnetogram, which was made in just from photospheric lines. So how does it compare with what we actually observe? Well, here's the comparison. These are the synthetic H-alpha absorption features, and this is what was observed at the time. And you see that some of the features are recovered very well. In particular, their slope is recovered very well. And that tells us we've got the location of the prominence is correct. This one is recovered quite well too. This one is not well reproduced, but the main features are there. Now, I said I had done this for a potential field extrapolation. I could have extrapolated the field in another way. This is one particular non-potential field extrapolation. In other words, there are volume currents that are extending out into the corona. You can see that although the surface magnetograms are the same, the field structures that are predicted and the locations where prominences can be supported are very different. And indeed, the predicted H-alpha dynamic spectra are very different too. So in the middle, we have the observations. On the left is the prediction from a potential field extrapolation, which you see recovers this feature and this one, although it fails to recover this one. The non-potential field extrapolation is quite different and is not a good match to the data. So what this tells us is that slingshot prominences can be used a bit like iron filings to outline the structure of the star's magnetic field. And we can hopefully use these observations to learn about how the magnetic fields in these stars are structured out in the corona, where we can't observe the magnetic fields directly. But what about winds? That was the other puzzle that I had. So in my last 10 minutes, I just want to talk about winds. This is quite a busy plot, so I'll take my time with it. This is mass loss per unit surface area, plotted against X-ray flux. And there are two different types of symbols showing on this. The purple squares are observations. So this is an ingenious technique pioneered by Brian Wood and his colleagues to determine wind mass loss rates from Lyman alpha observations. So all these purple squares are observational results, and the purple dashed line is the fit through them. And you can see the relationship down here. The circles are models based on the observed magnetograms. So these are wind models based on observing the magnetic field. And the black dashed line is the fit through those. You see that the models and the observations produce very similar slopes. But what I want to point your attention towards is actually the fact that these points are colored according to the mass of the star. And the very faint yellow color are the lowest masses. So we can see, if I highlight those for you, the lowest mass stars are the real overachievers when it comes to mass loss per unit surface area. They're very small, but they have, very, very distinctive, very powerful winds given their size. So what is it about these stars that causes this? And I guess as a theorist, I probably ought to come clean at this stage and be honest and say, I think this is fascinating that the little stars have these great winds, but there are no observational data points up here. All the purple observations are down here. So what we would really like to have is we'd really like to have some observations up here to test this theory. And this is where the prominences come in. So let me just give you a quick bit of background here. This is a model that we're looking down on the rotation axis of the star. This is the star in orange. The black dashed line is the co-rotation radius. And this flux tube here is a flux tube that has been allowed to cool down to prominence temperatures. And it's colored by the density of the gas that it contains. So it has reached an equilibrium shape. It's embedded in a background dipole field. And this is the shape that it has acquired. You can see all the mass accumulating out here because the star is rotating rapidly. It's acting like a centrifuge. Material is collecting at the very top of this loop. So we can determine quite easily what's the maximum mass that could be supported. We simply balance the gravitational forces up here with the magnetic tension. And we can express this as the maximum mass relative to the mass of the star. Depends on the ratio of the magnetic to gravitational energies, modified by the co-rotation radius, and there's a geometric shape factor. But what is fascinating about this is to think about what happens on the real star. Material has to flow from the surface of the star out to this point to form a prominence. But by the time it's even got as far as the co-rotation radius, it's supersonic. So the surface is unaware that a prominence has formed. Not only that, the surface is unaware that the maximum mass has been reached, the prominence has been ejected. it will just keep blowing material up the legs of the loop, and a new prominence will form. So for many of these stars, their coronae are so hot, the winds are so fast, that the prominences form and are ejected just in a limit cycle. So because of this, the rate at which prominences form and are ejected is essentially telling us the rate of flow of mass. It's just mass divided by lifetime. And those are both things that we can observe. So by observing the masses of prominences and how long they live for, we can infer the rate at which mass flowed into them, and therefore we can infer the rate at which mass was being lost in the entire wind. Now we have to make some assumption about what fraction of the surface is supplying the prominences, and we can inform that judgment by the Zeeman Doppler images that we have and the structure of the fields that we find. But on the right here, I've redrawn that complicated diagram, mass loss per unit surface area against X-ray flux. And up in this part of the diagram is where we had no observational data points before. And the prominences fill this area in really nicely. And it shows the trend continuing out to the very high X-ray fluxes that are observed for these stars. And this agrees really well with many of the different models that have been produced for stellar winds, and with the existing and the ongoing measurements of wind mass loss rates. So prominences are great as wind gauges in a region of parameter space where other methods are very difficult to use. What about prominences as stars age? I started off this talk talking about rotational evolution, the fact that stars spin down because their winds are carrying away mass and angular momentum. Well, we can take a simple rotational evolution model, and at each age point for the star, we can determine the masses of the prominences that could be supported. So this is a plot of prominence mass in grams against age in millions of years. And as at the start of the talk, the blue line is for the star that started off its life rotating rapidly, and the green line started off rotating rather more slowly. The colored areas are the times, the parts of the lifetime over which these stars could support prominences in their coronae. And the symbols are the observed masses for these are 5 of the stars. And you can see that although there's quite a large scatter in the observed masses, it lies within the predicted masses given the rotational evolution that we know of. But these are the prominences. They're not the coronal mass ejections. They're two different things. The prominences on the sun are much more low-lying than coronal mass ejections, although they're often entrained with the whole coronal mass ejection as it's thrown off. So what would we infer, or could we infer anything about coronal mass ejections? And I'm glad that Steve's in the audience. I've got his plot in this talk. So this is a plot of mass loss rates against time. And you see time going from 10 to the 6 years up to the present day. So the red dashed line is the predicted mass loss rate in the solar wind. And you see this constrained here by the observed mass loss rate at the present day. The blue lines are mass loss rates predicted from CMEs from the sun. Again, in the present day, these can be constrained by in situ observations. As we go back in time, it becomes progressively more and more difficult to constrain these. So these are the masses that you might infer being lost in coronal mass ejections. So how does that compare with the rate at which we believe young suns would be losing mass in their prominences? Well, I quite literally did a cut and paste to overlay the mass loss rate in prominences on top of this diagram. And so here we see our mass loss rate for our rapidly rotating star and the more slowly rotating star. So this is the mass being lost just in ejected prominences. And we can see that it's a small component of the predicted mass loss rate in CMEs, but it shows a very similar behavior in time. This, of course, is just for a solar mass star, and it's a fascinating question to wonder how different would this have looked for those M dwarfs. So I think my time is up. I'm going to stop here with just a quick summary. Slingshot prominences are good as windometers. They are good at measuring wind speeds. You observe their masses and lifetimes, and you predict the wind mass loss rates. And they're useful tracers of coronal geometry. From the observed magnetograms, we can predict the H-alpha trailed spectra, and from that we can compare with what is observed and use that to refine or perhaps destroy our models of coronal structure. And at this point I am going to stop and I can take questions. If I can get out of this, I can take questions. I think I can get out. Well, yes, I can escape.
Thank you very much, Moira. Nice talk. My question was on if you have in your hammer prominence analogy, I'm wondering, what does the spinning flaring kilt represent? Maybe that's a steamer belt.
Well, I do hope that we've got enough solar physics people here to get the joke. It's the heliospheric ballerina skirt, I would say. But I think it should be referred to as the heliospheric kilt. But that does lead to lots of jokes.
Okay, does anyone else have any questions? Yuta.
Thank you. Thank you, Moira. I'm Yuta from STU. Yeah, I have several questions, but I'll ask one question. You said from prominence observations, as X-ray intensity becomes larger and the mass loss rate becomes larger, and active. So you say more active stars have a more large mass loss, but in CME observation of the star and possible CME observation of the star, kinetic energy is much smaller than the solar case. How these two results correspond, do you think?
Well, there's a lot of interest in this.
Yeah.
The one possibility is that in these very active stars, they have very strong magnetic fields which act to confine coronal mass ejections. So although you have the flare, the star is unable to eject the mass because of the confining magnetic field. And that certainly is the suggestion that was put forward to possibly explain this. In fact, there's some nice modeling done by no, I'm gonna have to look back through my notes to find out. Alvarado Gomez and Jeremy Drake both done modeling of this.
Okay, thank you.
Okay, Jeff.
Yeah, very good talk. I'm really interested in the topic, and I just want to point out that there's a paper that was just submitted to the AppJ, of which we are both co-authors, on Hubble observations of the mass loss rates of M dwarfs measured with the astrosphere technique. And I just want to point out that one of the stars for which we have a pretty good mass loss rate estimate, star YZ-CMI, is right in the middle of the predictions that you're making from the slingshot. So I think there's a very good agreement among two different techniques, each of which have assumptions that go into them, but at least an agreement in this one particular case of the mass loss rates. Any comments?
Yes, if I had been confident the paper had been refereed to, I might have showed that point. I was very tempted, Jeff. But YZCMI also has been well observed. In fact, it was on the plot I showed for stellar CMEs. I think Jutta will know about this one as well. So I think it's a star that we ought to keep our eye on in the future.
Yeah. Well, anyway, the paper was just submitted, so we'll see what the referees have to say.
Okay, Arvind has a question in the chat. Do you want to ask it yourself?
Sure. On your penultimate slide, when you were talking about the rate of mass loss due to the different phenomenon, so you've got the curve for mass loss due to solar wind, you've got the curve for CMEs and for prominences as well. Are you distinguishing between the mass loss due to CME and then this slingshot thing from a prominence based on the physical origin of how the ejection actually happens? Or because if you're losing mass through, I mean, I guess a prominence just being ejected, I didn't really know how that would be classified as not a CME.
I have got into such hot water over the years from the solar community about the difference between prominences and CMEs. So the prominences are cold features. They're absorbing NH alpha. CMEs are hot. CMEs are incredibly fast moving. So I mean, typically on the sun, and I'm sure somebody is going to pick me up, somebody from the audience, if you have a large CME ejected, it's often associated with an underlying prominence being ejected, but they are two distinct features. Now, on stars, of course, we can't directly see the CMEs. The prominence is the one tracer that we do see of the mass being ejected. And it's quite possibly the tail wagging the dog in the sense that this prominence is probably a small component of the mass of the CME, but it's possible that the two are ejected together. So the prominence mass that is ejected is probably a lower limit to what is coming out in the CME. But the ideal would be to have the simultaneous observations that both showed us the CME being ejected and the prominence at the same time. But we're not there yet, sadly.
Cool. Thank you.
Phil?
Hi, Moira. I really enjoyed the talk. A lot of physics in that. I especially enjoyed your demonstration of the meaning of helicity through your potentials there. I just had one question about thermodynamics of prominences. It seems to me that you have to understand from Balmer alpha how to relate the n equals 2 and 3 levels to the bulk of the mass in hydrogen. And particularly for a diverse set of stars with different photospheric temperatures, I would imagine it's very difficult to estimate the mass of any prominence. I mean, it's notoriously difficult in the sun for a variety of reasons. And so, I'm just wondering to what extent you worry about that kind of thing.
I think it's an absolutely fair comment. I mean, it is done using the line ratios, and it's only been done in real detail in a couple of cases. Abidor is one of the best examples. So I think there's a lot of room to improve the mass estimates. But even using the same technique, the mass estimates vary from star to star, and that is not entirely surprising if you think of the physics of what would support those masses. If you have an order of magnitude in the field strength, you've got 2 orders of magnitude in B squared. Mm-hmm. So you can support 2 orders of magnitude more in mass. So I think although there's a lot of room for improvement in the way that we determine the masses, I think that even within that, the observational range over which we see them is large enough that it's still useful.
Thank you.
Okay, thanks. So we're at 1 o'clock, but is there any final question before we wrap up? Well, thank you again then, Moira, for a Great talk.
A great pleasure. I shall go and put my coat on now and spin around a few times.
I'm disappointed you didn't start with that.
You're not really. It's nice to see everybody. Bye for now.